잘 들리나요? 안 들리나? 예, 감사합니다. 오늘 Q&A를 할 텐데 아마 외국인 학생이 들어오면 영어로 하게 될 것 같아요. 근데 혹시나 이제 학생들 중에 질문한 게 제가 어제 보니까 크게 많지가 않아서 혹시 뭐 그걸 설명하다 시간이 남으면 다른 학생들도 뭐 질문할 것들이 있으면 챗룸에 질문을 해도 되고 아니면 음성을 켜고 질문을 해도 상관없습니다. 지금 질문해도 되고요. Okay. So I just said, I mean, we can start at 9:01, but if you have any specific questions that you didn't post, I mean, in the KLMS, then you can ask questions. Maybe now or maybe at the end, I mean, during a Q&A session or at the end of the Q&A session, anytime you like. Okay, so let's start. And I forgot to. Okay, so the first question that I want to discuss a little bit is the one that's posted by Robert. And so there are three questions that I found in the KLMS. So Q&A session. So the first question is, so what are the intuitions behind strictness, continuity, and monotonicity? So that was one of the questions. And then, so here are questions from KLMS. And the second question is, why should we study about category theory? And then the third question is, in the lecture notes, right after the categorical fixed point theorem, we talk about something called domain of embedding projection pair. So the question 3 is about a little bit related to question 2. And when it's discussed about category theory, we learn very abstract theorems. And actual application of this abstract theorem is done by this category of the embedding projection pair. I will explain what it is a little bit. And then in this category of embedding projection pairs, and the function space, the kind of morphisms or functions that we are considering here is not just continuous function, but also it has to be strict, so continuous and strict. And it actually has to satisfy more conditions. But then I think the Hachan asked, why should we, in this setup, so perhaps the right way to think about function space is going to be function from domain to domain that is continuous as well as strict. And he's just saying, is it the one that we should use instead of just domain of continuous function from D to D when we talk about recursive domain equation? So, why we are restricting morphisms in this category while we are considering the function space of just continuous functions? So this is the third question that I want to discuss. And as I said, if you have any more questions, then you can post in the chat box. Okay. So there are two others. The one is about getting some examples of using lists in described in the problem sheet. So I pointed out a particular chapter of the textbook. So if you look at that chapter, you will see a few examples. And I think some of you are familiar with programming with functional languages like Scala or OCaml. So then, for those of you, it shouldn't be any problem at all because it's just exactly the same kind of things, lists with nil and cons operators together with a pattern match. That's what's going on in the problem sheet. But for some of you haven't experienced with the list libraries in functional languages, then you can find information about it in chapter, I think 11.5. And there is one more, which is about the difficulties of the exam questions. And because, I think every faculty member in KAIST have a problem because it has to be a take-home exam because of the COVID-19. And then if you give a take-home exams, I think it has to be an open book and then also all the materials from the lecture should be available. And also you should give enough time. That means problems, becomes very difficult. So I try to pose not so obvious questions in my problem sheets. So if you find those problems are very hard, I just think that everybody will experience exactly the same. And low exam marks doesn't necessarily mean you're gonna get a low grade. So just do your best and everybody will be in exactly the same situation. Assuming that you follow the basic materials of the course, in the sufficient detail. Okay, so let's go to these questions. So what are the intuitions behind the strictness? Behind the strictness and continuity and monotonicity. So really, I think the question is about, we studied about the domain theory and it's specified mathematically, but what does that really mean computationally? But before talking about the intuition, let me tell you one thing. So these strictness, continuity, and monotonicities are properties of programs. It's a bit like, some of you may have studied the computability or complexity theory, and then in computability theory, we are saying every program that we are writing, they denote so-called computable functions, which can be characterized by Turing machine or can be characterized by some other material devices like recursion theory. So in the very same way, there's not strictness, but continuity and monotonicity. These are properties of a program. Every program, so all programs in imperative language that we study and functional language that we study. And I think in fact, nearly all the existing programming languages satisfy these properties. So these are the property which is not explained that often, but they are the properties, that's enjoyed by all the programs, okay? And because of, and strictness, in a sense, is a additional property that's satisfied by eager functional languages. So we didn't explain it this way, but this is a property that's satisfied by eager functional languages, okay? And then, so what are the consequences? How we can use, so these are like some property which people didn't really talk about very often, but it's true. It's satisfied by all the program. So how, where can we use it? And in domain theory, so, and when we give a denotation of semantics, we use continuity and monotonicity to ensure the existence of least fixed point. And then, in turn, this existence of this fixed point is used to interpret groups and recursions in imperative languages that we studied and functional languages that we studied. Okay, so I'm just saying these are not intuitions. These are, I'm just saying these are the properties, and noticing or recognizing these properties actually help us because it let us define the compositional semantics of imperative languages and functional languages by least fixed points. Okay, so then what are the intuitions? Let me start with the intuition for strictness and then monotonicity, and then move on to continuity. As I said, strictness is a property that's satisfied by every programs in eager functional languages, but in a lambda calculus with normal order evaluation, strictness sometimes true, and strictness sometimes doesn't hold. Okay, so I will use the lambda calculus with normal order evaluation to give you an intuition about what strictness means. So let me give you a conclusion first. What does strictness means? It means that strictness is a property of a function. It means that it always evaluates its argument. Okay. So that's what it means. Okay. So in some programming languages like a Haskell, which is based on normal order evaluation, sometimes these are languages employ so-called strictness analysis in that mathematically correspond to showing the function is strict when you interpret functions using denotational semantics. Intuitively, what it means is that no matter what happens, it always evaluates its argument. Okay. So let me be a bit more precise. So here's a quick reminder about domains for strictness analysis. No, not strictness analysis. Domain for lambda calculus with normal order evaluation. So there we use domain D, which is the V lifted, and then the V another domain was isomorphic to, the continuous function to D. Okay. This one is essentially because D is equal to V lifted. This is the same as V bottom to V bottom. Okay. So what does strictness mean? Strictness is a property about functions. So if you have a function f that goes from V bottom to V bottom, and then V and D are all at least pre-domains, and D is a domain. And D is a domain. So what is a strictness means? Strictness means is that it is a property of a function f. Strictness means if you give a bottom as an input, you produce bottom as an output. Okay, so I will give you some examples of lambda calculus term, which is strict as well as not strict. So here's the example which is not strict. Okay, so it takes argument x, but then it doesn't look at the argument at all. It just return identity. It's a result. Okay, so it takes x and returns lambda x dot y. This is not strict. If you give a denotation as interpret this term using denotational semantics, this is not going to be strict. Okay? And that corresponds to our intuition. This term doesn't evaluate this argument at all. Okay? So this corresponds to, So this is an example of non-strict when you interpret this as using denotational semantics and intuition. Then this example is the one where its argument is not evaluated. And then another example is lambda y, where maybe use x here. Lambda x applied to lambda y dot y. To evaluate this on the normal order evaluation, y has to be evaluated because we need to know what operator we are talking about. So this is a strict example of strict. So this is an example of a strict, and you can see that in the examples, this argument y is always evaluated. So intuition about strictness is to make this statement exactly is not quite easy, but roughly speaking, the strictness of a function f means that it corresponds to a program that always evaluates each argument. So if arguments go into the infinite loops, then it will go to, so it always corresponds to the function that evaluates its argument. Okay. So I think I have to say one more. Right. So then you might say, okay, why this, evaluating its arguments and then mapping bottom to top bottom correspond to each other. That is because if we always evaluate its argument, like this function, now suppose we apply this function to a lambda calculus term, which goes to the infinite loop. So I will write it like z-inf. That's a lambda calculus term that goes infinite loop. Actually, it's not z. And this e-inf exact definition goes like this. X. So if you evaluate this, it becomes itself. So if you keep going on forever. So this represents non-termination. So I'm trying to explain what so if it's an eager evaluation, then everything is strict. And then normal order evaluation, sometimes strict, sometimes not strict. Okay. So I'm going to explain why that's the case. So in the normal order evaluation, if you pass this argument for this is the second example, for the first example, okay, so for the second example, let's look at the second example. We have a x lambda y, and then it applied to E inf. And the normal order evaluation, although we will think about the small step, big step evaluation. Let me just write what's going on in step by step using contraction relation. So if you express it step by step, then in the normal order, we do not evaluate each argument, we just pass the argument. So we're gonna have E inf lambda y dot y. Now we have an application of E inf to lambda y dot y. In the application, regardless of whether we are using normal order or eager evaluation, we always have to evaluate each operator because without knowing operator, we can't do anything. So we have to evaluate operator, but this operator is the exact term. It's going to be lambda x, xx, then lambda x, xx. So this is what we have there. So if we evaluate each operator, which is this term, then after the evaluation, we're gonna get, we replace these two x's by this lambda x, x dot x. So if you do so, then here's what we're gonna get, lambda x, xx. That's because of this first x, and the lambda x, xx. That's because of this second x. Okay. And we have exactly the same thing. And now we are in the same situations. We have to evaluate the operator to figure out what operator is. So this one, exactly the same thing continues, go on forever. Okay. So what does this mean? This means that if we plug in an argument that go into infinite loops, the entire thing becomes an infinite loop. Entire thing goes into the infinite loop. Okay. So that's really captured by this expression, which is if we compute the meaning of this term, that's going to be a value in D, but the value in V actually, but this one, because of this isomorphism, that can be understood as a function f. But this function f is going to map bottom, which represents infinite loop, to bottom, which is also represents infinite loops. Because it's going to evaluate each argument. Okay, but on the other hand, the one above, if we do the this evaluation sequence or contraction sequence, the one above will immediately terminate because it's not looking at its argument at all. So in the normal order, in the eager evaluation, something like this always happens because in the eager evaluation, we always evaluate its arguments. Okay, and then we go on. In the normal order evaluation, we don't evaluate each arguments. We just do the usual computation, but it happens that at some point, the argument is forced to be evaluated, just like this second example. So this strictness really means, although normal order doesn't force us to evaluate the argument, this is specific program, or this specific lambda expression f is always evaluating its argument at some point, not in the application point, but in the middle of the computation, like the step that I showed here. Okay. So does that answer, Juyeon? Do you still get confused? Okay, good. So that's the idea of strictness. So just like, I think that maybe my explanation was a bit vague. I said evaluate the argument. Normal order, we don't evaluate the argument. I'm just saying arguments gets evaluated after the function application at some point. If that happens all the time, we say the function is strict. Okay, so that's the property. Then now what's the monotonicity? 3. Right, so say 3. So what does the monotonicity means? Monotonicity, mathematically, it's really simple. Right. So if you have a function f that goes from free bottom to free bottom, and then if you say function f is monotone, that means if you have we get always this if a is smaller than equal to b. Order preservation. So mathematically, it's really simple. So computationally, what does that mean? So this means that, I said monotonicity is an intrinsic property of a program. It's always true, okay? So let's try to figure out what does that implies for me in terms of a program. So let's look at two programs. So we have a program E that takes, if you apply this program in the lambda calculus on the normal order evaluation with the identity, we found that this goes to the infinite loop. Okay, so now suppose it's a normal order evaluation, so it doesn't necessarily evaluate its arguments. But above one, it went to the infinite loop. And then maybe to make it more complex, we apply this E, and then another ID. We went to an infinite loop. Now we change this program slightly so that for the second argument, the first argument, we replace it by this EINF. Okay. And then the second argument is the same. Then we can ask the following question. Is it going to infinite loop again? Okay. If you look at that question, looks okay. Looks like it should go to the infinite loop, but who knows? It may be not going to the infinite loops, but it's not entirely obvious. But the monotonicity tells us that this one, the answer is always yes, because of the monotonicity. Okay, this doesn't tell you that monotonicity is, what are the intuition about the monotonicity, but it tells you, if you know the monotonicity, it can at least help you to understand what's really going on without really looking at this particular program E. That is because we know that every program will satisfy the monotonicity. Intuitively, here what I'm talking about is a bit vague, but this is a typical explanation about domain theory. This less than in domain theory models this B is more informative. It represents more informative computation or value than A. Okay, what does more informative means? This, if we have some number 3 is more informative than going to the infinite loop, because if you go to the infinite loop, the bottom represents typically going to the infinite loops. But if you go to the infinite loop, you don't get anything. If you, from the perspective of the output, you don't really get any output at all. So information that you are getting is 0. It's really nothing. But if the program produces number 3, that produces some information, which is the outcome is number 3. Okay. So this less than relation in domain theory means that something larger like a B provide more information than something smaller like A. Okay. Another example of domain is we think about, this is not, well, okay, we can think about functions. We can think about some function that always take value, always return bottom. So it's a function, but whenever it's applied, it go into infinite loop. So sorry, change this. Okay, so it doesn't provide information at all, but if you write it like this is more informative, because previously, if you apply the function, it doesn't return any output at all. At least give some information, which is provided the information is just input free. Okay. But there is just input free. Okay. But there is no order relationship so between the one that I wrote here and another example like v bottom, and then maybe lambda y. Okay. I just okay. Yeah, let's not worry about that one example. Okay. So this the less than means more informative, and then monotonicity means that if we apply function represented by a program or implemented by a program, and if you apply the function to A, also if you apply function f to more informative input B, then output will be more informative for f of B. Okay? So that's what the monotonicity tells us. So monotonicity say my program is preserving this, this information, the information relationship. Okay? More informative inputs leads to more informative output. So that's the intuition behind the monotonicity. Continuity is more tricky. Okay. So in some sense, continuity and monotonicity, they are, if we are really defining everything that we are writing in programs as using Turing machines and computable function and so on, they all follow that monotonicity and continuity are, in a sense, approximate version of you can understand them as approximate version of computability, but it's much more kind of, you only talk about input output. It doesn't really talk about what's really happening in the middle. So it's much easier to deal with mathematically. And continuity is also captures another aspect of the computation. Okay. So what does it tell us is it continues. So if you have a function f, which is if it's continuous, if and only if, in order to produce a finite amount of information of the output, of f, we just need maybe it's better to just say from the perspective of f. In order to produce finite amount of information of the output, f just uses a finite amount of information of the input. Okay, so right. So think about, I think to one way to understand, the typical example that explains this quite well is that think about some program F that takes infinite stream. So it's a stream processing. So you take infinite stream like 3 infinite sequence to 4, 5, 7, and so on. In typical language, you can't do it, but in functional languages like Haskell or even like a closure, you can do this. Suppose f is given the infinite list, and then you produce infinite output. List as an output. Then you may ask the following question, because giving the infinite list as an input, producing infinite list as an output will take forever. So in practice, what's really happening in a programming language is you produce this infinite output list in a lazy manner. So infinite input list is produced, but it's not exactly computed. It's all written in a lazy way. If somebody look at, say, 10th element, that's the time value of the 10th element will get evaluated. Output is the same. If this sequence is not computed, I mean, only when somebody asks, I'm interested in like a 20th element, that's the time we're gonna do the evaluation. Another way to think about it is that we have an iterator. We give an iterator over an infinite sequence as an input. So iterator doesn't really produce this infinite sequence. It just tells us, okay, what's going to be the first element, second element, if it's asked. But it doesn't really produce in an eager way. Okay, it's very lazy. And then F returns another iterator as an output for the infinite sequence. Okay, now suppose that for such a program F, whatever mechanism we use, we say, okay, I'm only interested in, say, first 3 elements. Okay. And then we may ask the following question. In order to produce these first 3 outputs, how much amount of inputs this F looked at? If you give a mathematical definitions of this mapping from sequence to sequence, 4, 5, 7 may have been produced by looking at the entire sequence. Okay, there is an example like this in mathematics. If you take limits in the mathematics, then those limit operations really look at everything in the entire sequence. Okay, so you may ask, can that kind of thing happens in a programming language? Continuity tells us no, you can't really do this. Okay, so continuity with respect to appropriate order in this context, that if you are interested in finite amount of output, which is a finite prefix, then the function f to produce finite amount of output, function f will only use finite amount of input, which means that it will only look at the finite prefix of the input sequence. It can be 3 to 4 up to 7, or it can be very large. It may look at 1 to millionth elements, but it will always be finite. Okay, so that's what this intuitively continuously tells us, and that corresponds to our understanding. I mean, program has to terminate. So if we say I want to get number 4, 5, 7, I mean, program F cannot really look at every element in the infinite sequence because it's going to take forever. The only way for F to produce 4, 5, 7 in the output is to just look at only finite prefix of the inputs and then compute this 4, 5, 7. So this continuity captures that type of idea in a very abstract way. Okay. So let's look at the more concrete examples, 2 examples there. So when you give an interpretation of a while loop, you see, and we said the semantics of a while is defined by list fixed points, bottom of some operator capital F applied to sigma, and capital F was a function that takes sigma to sigma bottom, continuous function from sigma to sigma bottom, and then it's defined like this. F give us this function, the function from sigma to sigma bottom, and then that's going to be another function. What it does is it evaluates loop. If loop condition is true, then we go into the loop. That's modeled by first apply the body of the loop, and then apply this given function f lifted. Otherwise, we get out of the loops, and then we return to sigma. Okay, so that's what we use. And then important bit here is we are using continuous functions. And because it's a continuous, we can take a little list fixed point. So that's, in a sense, use of continuity. So now let's ask what this continuity actually means here. Okay. So if we said this f is continuous, and you can prove mathematically this f is continuous. But what does that actually mean? It means the following. So suppose we have we evaluate this f of applied to small f. Okay. Now define some function. Let's define 2 states, 2 specific states, sigma 0, sigma 1. There are states, And state is a mapping from variable to values. So sigma 0, for every variable, it returns 0. Sigma 1, every variable, it returns 1. Okay? So they are very simple states. Every variable returns 0, every variable returns 1. Now, before going there, let's try to understand this function f as a more like a computer science perspective. Function, this f is a mapping from sigma to sigma bottom, and sigma is a set of states like the one that you see here, and there are infinitely many sigma. Okay, and actually, I think there are uncountably many sigmas, and then we have also a sigma bottom. So one way, some imagine it's not implementable, but one way to think about this function f is a really, really large table. So so what is f? F is a really, really large table. So infinite with infinitely many entries. And then each entry say if the input is some sigma 0, it has to return bottom. Input is maybe say sigma 0, it returns sigma 1. Maybe it returns given sigma 1, return bottom, some other sigma 2, it returns some sigma prime, and so on. So it's a really large table which have uncountably many entries. Okay, so we can say this function f is really infinite entity, like this infinite sequence that we talked about here. Now, so think about some very simple, much simpler table, which is G0. What this G0 does, it's also mapping from sigma to sigma bottom. So there are many, many entries, but it's very simple in the following sense. If input is a sigma 0, it will return sigma 1. Okay, but for otherwise, for other sigma 1, for all the other cases, it will always return bottom. So then you can see that although this table is infinite, we can implement this. We can just say if sigma 0 is, input state is a sigma 0, return sigma 1. Otherwise, we always return bottom. This is implementable in a machine. The one f is not implementable, it's infinite, but the one below is really finite. It's a really, in some sense, finite case. So we can, that's an implementable finite case. Okay. So then this idea about continuity said, given finite, in order to produce a finite amount of information of the output, f just need to use finite amount of information of the input. Okay, so that corresponds to a property like this if G0. So suppose G0 is smaller than equal to capital F of f. So what does this mean? The capital F of f, this itself is also another infinite table. And then we are really thinking about some small infinite table. If G0 is less than equal, this relationship means we know capital F of f, small f, maps sigma 0 to sigma 1. But for all the others, we have no idea. So we are, this order relationship is really saying the sigma 0, how sigma 0 entry is behaving. Okay, so we are picking only very finite piece of information of the output. So then continuity will tell us to get this finite piece of information, which is a Z0, we only need to look at finite piece of information of F. So that's going to be, it may be just one entry, like a sigma 1, or maybe multiple entries, sigma 2 and sigma 3, but only finite amount of information is necessary to produce this G0. So continuity in this context implies the following property. If G0 is less than this, then there exists some F0, which is smaller than equal to F. such that it satisfies two properties. G0 is still covers G0. In other words, if you apply capital F to small f0, the sigma 0 entry will continue to be mapped to sigma 1. Okay? But furthermore, here's an important property. Only finitely many entries of f0 are not going to be bottom. Okay? So that's the property that we can get. Okay. So let me mention two more things and then move on to the next question. So then the one more thing I want to tell you is that another examples that, actually this is the kind of things I explained using more abstract examples in the lecture notes. The example that I use is that if you think about some function f that goes from the power set of 2 to power set of so all the subsets of I think yeah, so all the subsets of n to all the subsets of n. So this means and then suppose f is monotone. So the subsets are ordered by subset relationship. F is monotone. So then the following property is true, which is f is continuous if and only if for A subset of n, for B, which is a subset of n as well, but it's finite. So B is a finite if B is a subset of f of A, then there exists a finite subset A0 such that B is still covered by f of A0. So that's the very same thing to produce a finite amount of information in the output, which is B. We just need a finite amount of information in the input, which is A0 here. Okay. And there is a much more abstract way to explain what's really happening, which uses compact elements and algebraic CPU and so on. And I don't want to go there, but continuity really means to produce really means to produce some kind of finite things in the output. We just need the finite things in the input. Okay. Then technically, this is a property enjoyed by every program. That's because computation is essentially finite. We are not really thinking about spending infinite amount of time. And then we are exploiting this property in the least fixed point theorems to interpret loops and recursions. Okay, so that's a long answer for the first. Now let's move to the second part. Why we want to talk about category theory, and then also something about this domain P. And the answer for the reason we think about the category theory is related to this recursive domain equation that I showed you. So that's the equation that I wrote here. Right. So that I wrote here. So let me write it in a bit different form below. So the equation was domain D is isomorphic to continuous function elliptic. So this is a recursive domain equation. Okay. And then I said, this find showing there is a non-trivial D. Actually in this case there is a D at all. It's not very obvious at all. Just because if you take D as a set, then you will never have some set D which is isomorphic to, satisfy this isomorphism, where this arrow is just a set of all the functions. So we developed the category theory. We looked at category theory. Main thing that the key message of the category theory is what I call categorical fixed point theorem. And it's a bit like a tools. We studied why, what does that means and why it's true. We say that in order to show some construct something like a D which satisfies this isomorphism, it tells us what we need to do, okay? So the reason we studied about category theory is to find or construct this something like a D. So the proof of categorical this fixed point theorem tells us how to construct D. Or if you're just happy with the existence, this theorem ensures that such a D exists. And now how we do it? So to do this, to really use in our context, we have to instantiate this categorical fixed point theorem in our setting. And that's done by this domain of embedding projection pairs. So this is a new category. We have to instantiate this categorical fixed point theorem in this new setup. And that setup will let us use this theorem to construct something like D that I wrote here. Okay. Now, what are the actors? So I will just give you a kind of brief idea about how these things are done. To apply categorical fixed point theorem, we have to do two things. One is we have to fix the category C, which have initial objects, and also should have a colimits for all omega chains. Okay, these are the two conditions. And then we also have to define functor F that goes from C to C, such that functor F is omega continuous. So then we can apply the theorem. Okay, so now how can we, so then to construct this D that I mentioned here, and then solve the isomorphism, the recursive domain equations. So what we have to do is we have to instantiate D. We have to find the appropriate definition of this category C. Also, we have to find appropriate definition of this functor F. And then that's what's being done by this DOME EP. So that. So how should we instantiate C? So this C is really in our application. C is what I call DOME EP. Okay. What's this category? This category, objects in this category are domains. They are not predominant, they are domains. And morphisms are not continuous functions. They are morphisms that goes from domain D to D prime. They have to be continuous, but also has to satisfy more property, which is you should have something called, and then there exists another continuous function G that goes from D prime opposite direction, such that if you first apply F and then G, that is an identity on D. And if you do the opposite direction, G apply F, that has to be less than or equal to D prime. So what's going on here? What's really happening? This F is something really, really special. Okay, and this condition, it implies F is strict. So that brings the question of Hechans with the But that's the reason I think that Hechan asked the question. Okay. So what this morphism really means? This morphism really means that this D, I mean, it's not exactly the same, but intuitively what it means is this D prime, it's really saying D prime is obtained from D by adding some element on top of some existing element. So if we draw a picture of visualize D, so say, let's just take for the this integer bottom, 3, 4, so on. So suppose D is equal to Z bottom. So then if we want to define function f together with something like g, then D prime should be of the form. It should be the one that adds some extra element. I mean, first, this function f should be injective. So f shouldn't really merge existing element to the same element. And then D prime can add some element on top of some existing one, like a number 3. Maybe it adds 3 prime, 3 double prime, and so on. Like here, write it using some other color. Like here, maybe 4 case, we just add just 1, 4 prime. 5 case, we may add 5, 2 prime, 3 prime. Then we add all of them with the same one. So we can add something like this. And then this G is a mapping that maps all these if it's existing, so that's this is an extended D, so it's a D prime. And G is a projection. It maps every element to the most close approximation in D. So 5 is going to be mapped to itself because that's same, I mean, the close approximations in D. 5 prime will get mapped to 5 by G. 5 double prime is mapped to 5 and so on. And then 4 will be mapped to 4. 4 prime will be mapped to 4 by G and so on. Okay. So this F and G are called embedding. And G is called projection. That is because this D prime acts like, I mean, if we have this F with these conditions, D prime can be understood as extended version of D, and then G can be understood as really a projection. It projects every element to the closest element in D. Okay. So that's the setting, and then we instantiate C to be this domi P. Then it turns out this domi P has an initial object, and then also has a co-limits of all omega chains. And then furthermore, it turns out there's something very easy, some kind of tools which we can use to check something is a co-limit or not very easily. Okay. So it has some nice property. It meets all these two conditions. Now for F, we can define F as a functor on dom EP to dom P in this example, like this. So if we take some domain, I'll write it as a D prime so that you don't get confused with the D above. It can be written as continuous functions from D to D, okay? And now, to define a functor, we have to say how objects get mapped. So objects are domains. We say domain D prime will get mapped to this continuous function space to extend it with bottom, lifted with bottom. And now we also have to say if we have a morphism F that goes from D prime to D double prime, it has to be a morphism that goes from F of D prime to F of D double prime. Okay. And then because we have this F is a embedding, there is a projection G that goes in the opposite direction. And it turns out this projection is also unique. Continuous function. So And then using this G and F together, we can define this, this mapping that goes from this embedding that goes from, I think I'm becoming more and more complicated. It gets more and more complicated. But the point I'm making here is we are really instantiating this general categorical fixed point theorem to a specific example. And that specific example is this DOM EP. And then specific functor that we are using is this functor f, where for domains it acts as you expect. Just right-hand side of recursive domain equation. Left-hand side, we use, because we have a embedding and projection, we use both embedding and projection to define appropriate morphism actions. Now, once you do this, we can also show this is omega continuous. So because of this property, both of this category DOM EP has an initial object, core limit of all omega chain. F is the omega continuous. So by categorical least fixed point theorem, and maybe I just say categorical fixed point theorem. Can't erase this. Okay, right. So I said this is omega continuous. And because of these two properties, we can use a categorical fixed point theorem. And then what does that tell us? That tells us there is a morphism from f of, there exists object d prime. And then furthermore, this theorem says there is an object d prime and the morphism eta that goes from f of d prime to d prime, but such that many properties, and one of the properties is isomorphism. What does that mean? This means that d prime is isomorphic to f of d prime. Now, if I unpack this definition of f of d prime, that's going to be d prime like this, exactly the one that we want to talk about. Okay. Now the last bit is now Hachan asks, why should we really think about some older continuous functions from d prime to d prime? Because given that our category C that we are using only have embeddings, so shouldn't we only think about embeddings instead of all continuous functions? So the answer to that question is that here we are not really trying to characterize the morphisms in the category DOM EP. We are using this DOM EP to show the existence of the recursive domain equations that we care about from the beginning. Okay, so the theorem doesn't really tell us, and so anywhere it doesn't tell us, we have to use. We have to make sure this function space and then these embeddings, these morphisms should correspond to each other. Nothing really tells us. As long as we have well-defined functor, things are all work out fine. So technically, it doesn't cause any problem. And then also our objective is to solve this recursive domain equation, not the one where we only consider embeddings. Now, nothing is free in the world. So if you just do this, then there is some price we have to pay. 감사합니다. So some price we have to pay. The price we have to pay is the following. So if you look at this categorical least fixed point theorem, it has a two part. One part talk about we have a eta is an isomorphism, but the second part says something a bit like this d prime is a least fixed point. So in some sense, okay. And what does this sense means? This sense means that if we have any other objects d0 and any morphism, say row that goes from f of d0 to d0. Okay. So let's say if we have any other object d0 in category of domain P, and then we have a morphism row that goes from the f of d0 to d0. So it's also in isomorphism in domain P. So then there exists, or there exists a unique, it's called kappa, that goes from d prime to d0, which is a morphism in domain P, such that following diagram commutes. To say we have f of prime goes to prime. So it's a kappa, of kappa, there's eta rho. Diagram commutes. So this kind of means that we have a least fixed point among the, this is roughly corresponds to a prefix point. Among the prefix point, we have something list. Now, you might think that, oh, this is just some abstract thing, but actually we are using this, okay? So whenever we want to define some map, so say I want to define some map on D prime, okay, that does something. How should we do it? And it's very difficult because D prime is defined, this theorem say it exists but doesn't tell us how it actually look like. We have to look at the proof and then see how D prime is constructed. That's one way to do so. But this second part talk about how we can actually define a map that goes from D prime to something. And we, throughout the course, although I didn't point it out explicitly, we implicitly use some of these kind of functions. Okay. Now, how to define a map that goes from D prime to D0? Is the second part to say to define so, you just need to define row that goes from f of d0 to d0. And it has to be embedding because we are playing with the domain, the category of domain P. Once you do it, this kappa will exist automatically. And again, although I didn't really say this, when we talk about initial algebra and morphism there, initial algebra, and I said because of initial algebra, we can do the syntax-directed definition. That's exactly this is exactly the same principle. So really categorical formalization of initial algebra is really this kind of morphism. But anyhow, this is the same principle. And it's just said, if we wanted to define some map that goes from D prime, all you need to do is just define a morphism here. Once you do it, then we are done. Okay, that's what this one is to say. But now, because we are using this specific category, domain P, where morphisms are all have to be embedding, we have to be sure, in order to use this device to define this map kappa, we have to be sure what we are defining row has to be a embedding. Okay, so although I don't think it's possible, although if we do all these things in the usual category with the usual continuous function as morphism, so then we could have used instead of embedding arbitrary continuous function. That would have made our life a lot easier. But this categorical tool say, you can't really do it. All you can do is we have to always to use this device to show kappa. You have to make sure that what you are doing should meet all the requirements of the embedding. Okay, these are the long answers to these three questions. Does anybody have more questions? So I'm done with what I prepared. Does anyone have more questions? Okay, so it looks like so I think the Seungmin's question is not. I mean, it's good, but it's a bit requires some more explanation. Okay, Seungmin asks, so what are the relationship of the initial? I mean, I said initial algebra, but why we use this word initial here? Okay, I said the category theory. That mean we use initial for something specific. So the intuition is that so here's intuitive answer is initial means something starting. So the unique existence of homomorphism correspond to this initiality. So some vague answer. Homomorphism. This corresponds to initiality. But here's a more accurate answer. Okay. So really, if you formulate initial algebra as using categories, I mean the proper formalized, maybe universal algebra people will do something different, but one standard formalization of initial algebra or universal algebra is using categories. So in a category, so we can define, when you talk about this initial algebra and so on, maybe we can do it using what you can do it more abstractly, but let me just use something reasonably simple. You can use a category of a set. So this is a functions as morphisms, and we can and then for this abstract grammar, that we talked about. So it can be written, I mean, has to be a bit more maybe defined, but it can be written as a functor on set. Okay, how does it do it? So if you say abstract grammar of say expression, let's think about something really simple. Okay, so integer expression, which have an integer and integer expression plus integer expression. Okay, so if you have something like this, so then what the functor you can define is that, say, functor f. No, I forgot. Yeah, functor. Yeah. Functor f is defined like this. It takes any set S, and it returns the new set, which is obtained by a set of integers together with set S cross S. So this S cross S corresponds to this case, Z corresponds to this case, this bar corresponds to the one below. So once you do it, an algebra, so what the categorical notion of algebra is just a morphism. So more generally, all these things can be talked about any functor f on set, the category of set, or any other category. An algebra of f is a morphism in set that has the form f of some set x to x. So this is very abstract, but if you just think about it a little bit, you can show that. I mean, this really corresponds to what I mean by algebra. I mean, this is an abstract grammar, and I think in the lecture I also talk about what it corresponds to signature. So this eta corresponds to what I call the structure in the lectures. Okay. So more abstractly, the algebra is a morphism that goes from f of x to x. And then now we can form a new category where objects, there's a category of algebra where the objects are in these kind of algebras. And then morphisms are algebra homomorphism. So morphisms are algebra homomorphism. What that means is if we have one object, eta to x, another object rho that goes to f of y to y, morphism that goes from here to here, so g, that's a mapping function from x to y, such that this diagram commutes. And this commutativity corresponds to so where are we at? So I said the categorical formalization of this algebra is category to if you have a category together with a functor, functor corresponds to signature, what I meant by signature. And then algebra is just a morphism of this form in the category. And then using these algebras, we can form a new category where objects are algebras and then morphisms are algebra homomorphisms. So if you do it, then the what we call initial algebra corresponds to initial object in this category. So it corresponds to initial object is really correspond to initial algebra. So what they mean by initial means exactly the same. So in the textbook, John Reynolds sometimes called continuous initial algebra. That is because his underlying category he's using is not set, but a category of, I don't really work it out, but likely what he's using is category of pre-domains and continuous functions or category of domains and continuous functions. So that is what he's using, and he's following exactly the same recipe there. So that's why he's calling continuous algebra or continuous initial algebra. I feel like I make all of you confused, so, but I hope this would help a little bit. But there is a deep connection. Just one more question if you have, otherwise we'll finish. Okay, so then that's it for today. And on Wednesday, as I announced, there will be no lectures. And so we will have an exam on Saturday. Yeah, I wish you the best. And thank you all for working hard. The course is, perhaps might have said it or maybe not. Course is was not very easy, but I'm grateful that you work hard to follow this difficult course. Okay, so thank you very much.